Okay, hello, how are you doing? So we're done with your test. So our next target is going to be, okay, quiz number 3. So what we're going to do, we try to get more from for the series. Okay, we get quite a lot to do in this chapter 11. So we give you so far what we did. We just checking the definition of the series, and we consider a type of geometric series, telescoping series, P-series, and we try to see if the series is going to be convergent or divergent. As we move on, we need more theorems. There are some series that's not going to be geometric or maybe telescoping one. So we continue to give you more theorems or tests. So this is, we go with 11.3. There is a new test, we call it integral test. And before that, I'm going to tell you that what is going to be the direction of our argument to get through various tests. And at the end, if the series is given to you, you'll be able to answer that question right away. You see, this is the one that I talked about several times, but I'm going to post it for you. This is all the theorems that we need to be able to get to test or to tell whether a series is going to be convergent or not. So far, this is what we did, and I talk about it. You see, this is the one we call it n-term test. Remember, we check the limit of the an and goes to infinity. If this limit is not going to be 0, so the series is divergent. Okay, then geometric series, that's a general term. If the common ratio is less than 1, so in that case, the series is convergent. Otherwise, the series is divergent. If the series converges, as we talk about it, the sum of the series would be a over 1 minus r. R is the common ratio and the a is the first step. This is the telescoping one that we did. Okay, the telescoping series, the general term is the difference of two consecutive terms. So we just we simplified and we end up with the b1 minus limit of the b, and we can check this one. If the limit exists, then the series would be convergent. P series, we already talked about it, is 1 over n to the p. P is going to be a fixed number. If p is bigger than 1, the series is convergent. And if p is going to be less than 1, the series is going to be divergent. And there are more to go. So what we're going to do from now on, we are going to check into these. And at the end, and when we get to your quiz 3, then we learn all of them together. So if the series is given to you, then you'll be able to tell us whether it is a convergent or divergent. When I finish it, then I give you a hint, a chart that how we're going to check it. So far, there was so famous one, and you did check it on the test. Okay, but we need more to go. When you need more, when we get the more, then we'll be able to go back and check it. There is one that here we call it integral test. This is the one we are going to talk about it tonight. Okay, and that would be section 11.3, and the rest going to be 11.4. Okay, so this is how we're going to continue to get this series. And at the end, it will be, when we have all of them, then I can tell you how you're going to handle it. Okay, so let's see what's going to be this this famous integral test. So that would be 11.3. This can be used for very typical series, and sometimes this is the one that we may ask you. We may ask you to apply the integral test to take care of it for us. Okay, so we want to know what's going to be integral test. Integral test. So remember we talked about improper integral before when we get integral 1 to infinity. So this would connect these two together. So that's going to be what is going to be the integral test. So suppose you have a function. Okay, we check the condition of this test. So suppose f is a continuous. F is going to be a continuous. continuous, one condition, positive, is the value of the function going to be positive, and decreasing function, and decreasing function. So three conditions that you have to check. See, first one, this must be continuous. The second one, the value of the function must be positive. The third one, the function must be decreasing. Decreasing means as you go on, the value of the function getting smaller and smaller. So if this is going to be this function on the interval of 1 and infinity, okay, this one you can change it into, the one is good for the series, but you can change it to the 2 or 3. If this is going to be the case, then, okay, then this is the situation we have. Then you can make a series with the general term of f of n, the function, n from 1 to infinity. You see, if this is going to be the case, this series is convergent. It's going to be convergent if and only if. If and only if the improper integral. You see, the improper integral. Integral 1 to infinity of f of x dx is convergent. So this means both of them can be convergent or both of them can be divergent. So what you're going to do if this series is given to you and you've been asked to apply the integral test, so what you're going to do is you are going to call your general term, you call it f of x, then you check to see if this function is continuous, this function is positive, this function is decreasing. If these three conditions satisfy, you work with this integral. You know that this is integral 1 to infinity. You change to infinity into a fixed number like t. You integrate it. You find the limit of the result. If the limit exists, integral is convergent. If the integral is convergent, your series is convergent. If your integral is divergent, the series is divergent. Okay, so it's a connection between both of them. It's very nice, nice result. It was proved by, okay, by Cauchy for the first time. So let's get the example to see how we are going to check this one. Okay, example, we want to determine, you see, determine if the series, okay, this is it, converges or diverges. With this test, you can only tell us whether it's convergent or divergent. You cannot find, of course, the sum of the series. Okay, the sum of the series so far can be found if it's telescopic, okay, or it is going to be geometric. So we just give you some famous result that previously we asked you to accept it for the time being. Now we can prove it. Remember this series, sigma of 1 over n is a p series, p equal to 1, or is a harmonic series. You know that this harmonic series is divergent, but if you want to prove it, you can prove it by the integral test. Okay, so how are we going to prove? You change it into a function. Okay, you change it to the function. So what you're going to do, you're going to define, say suppose. Okay, suppose you change it to the function f of x is going to be equal to this general term, 1 over x. It's going to be 1 over x, x from 1 to infinity. So x can be any number greater than or equal to 1. Okay, now you check the condition that we have. Continuous, you know that 1 over x is continuous because it's continuous when x is not equal to 0. But your x is from 1 to infinity. So this would be continuous. Positive, x is positive, so 1 over x is also positive. So this function is positive. Decreasing, you see x greater than 1. So as x getting bigger and bigger, 1 over x getting smaller and smaller. So the function is decreasing. So you have to explain it. tell us the condition. So we say that then, this is clear, sometimes you have to prove it. Then f is a continuous, positive, and decreasing, function, okay? Decreasing function on this interval of 1 and positive infinity. You see, you exactly check the condition of the theorem. The condition of the theorem, f continuous, positive, decreasing. So now we test the improper integral. Test the improper integral to see if that integral is convergent or divergent. So we check the integral from to infinity, f of x dx is going to be integral from 1 to infinity, 1 over x dx. Remember, you change it to the limit. It's going to be the limit of what? Limit of 1 to t. T goes to infinity. The function 1 over x dx. You know that 1 over x is the derivative of ln x. So this is going to be the limit. The limit of what? The limit of ln x. X goes from 1 to t. Okay, then you take the limit when t goes to infinity. So you substitute first, going to be the limit. It's going to be ln t minus ln1. Okay, when t goes to infinity, ln of 1 is 0. So that gives you the limit of, you see the limit of ln t when t goes to positive infinity. You know that. Ln is the increasing function. So when t goes to positive infinity, this would be positive infinity. Okay, so improper integral, you didn't get any number for it, so the integral is divergent. Okay, so the improper integral diverges, and you can say that by the integral test. You have to mention the test, the name of the test. So by the integral test, the series, okay, series of sigma of 1 over n from 1 to infinity is what? Is divergent. You see, this is the proof. We already had this information that this is harmonic series, but we didn't prove it for you. So now you can prove it to get this number. Okay, so this is going to be harmonic. You can do this one for any power series. Remember, we talked about it. If p is bigger than 1, the series is going to be convergent. Let's take another one to make sure you know it. And this is exactly the way we prove the convergence of the power series. Okay, so let's have another one. For example, you want to check this one, number 2. Another power, you know that you check this series. Okay, so sigma of 1 over, let's say, n cubed, n from 1 to infinity. You know that this is a power series. It's a power series, and the power n is 3 bigger than 1. By the p series, sorry, this is a p series. It's by the p series, it's convergent, you know that. But if you want to prove it with this test, this is the way you're going to do it again. You introduce the function. Okay, you suppose f of x is going to be equal to the 1 over x cubed. Then when x is greater than or equal to 1, then you argue that f is continuous because x is not equal to the 0, x starts with the 1. So this is continuous, it's positive because x is positive, so 1 over x cubed is positive. It's decreasing because the denominator is getting bigger and bigger, so the function getting smaller and smaller. Okay, so you say that f is a continuous. You have to mention this one if you've been asked to use the integral test on the next test. F is a continuous, positive, and decreasing function, okay? Decreasing function. Okay, this is going to be the case. So you check the improper integral. So improper integral of 1 to infinity f of x dx is equal to the 1, sorry, you have to use the limits. Oh, okay, it's going to be 1 to infinity. Let's substitute first. 1 to infinity, 1 over x cubed dx. So the definition, change it to the limit. So it's going to be limit t goes to infinity, integral of 1 to t. Okay, you move this one up to integrate it. So that's going to be the 1. Integral of x to the -3. So it's going to be limit of, okay, t goes to infinity. And this integral is going to be what? X to the -3 plus 1, which is a -2 over -2 to be evaluated from 1 to t. So x to the -2, you bring it down. So it's going to be limit of a fraction, -1 on the top, 2x squared on the bottom. Okay, when t goes to infinity, but this is going to be evaluated from 1 to t. Substitute first when we limit. Okay, t goes to infinity. You put the t first, -1 over 2t squared. Okay, it's going to be minus, when you put the 1, that gives you -1 over 2. You see, this is going to be the result. Negative would be positive, so this is going to be the limit of t goes to infinity. And this is a -1 over 2t squared, and this would be a positive half. Now when t goes to infinity, you see this one, the number that would be infinity, it's just a pizza problem that we did before. So this goes to 0, so the limit would be 1/2. So integral is equal to the 1/2, so this means the improper integral is convergent, so the given series is convergent, okay? So you have to argue that the improper integral converges again and by the integral test. The integral test, the series sigma of 1 over n cube is also convergent. So it's a kind of one-to-one correspondence between the improper integral and the series. Look at this one. This is the one that we call it integral test. You can bring this one page to any test or the quiz from now on. It would be very useful for you if you want to remind yourself. You see, that's the case that we have. That's integral test. If the integral 1 to infinity f of x dx converges, okay, if this is convergent, the series would be convergent. If this is divergent, the series would be divergent. So we are here. We just proved the integral test. Okay. Now, this example is usually used for some very typical series that you have no other method to do it, and that series would be of this category. I give you one, then I write something more general for you, okay? So the number 3 is this type of, I gave you this one before. I told you I'm going to use it 4 times. So this is it, the series of 1 over, it's going to be n here, then ln n squared, ln n to the 2, 3, 4, 5, 6, etc. So let's check ln n squared. N, of course, cannot be started from 1 because ln of 1 would be 0. So we started from 2 to infinity. You see it's going to be n here, ln of n squared to the 3rd to the 4th, cube root. So this is very typical problem for the series. And the only method is integral test to take care of this one. So you see why. Solution. Introduce a function. So suppose f of x is going to be equal to what? It's going to be 1 over x. ln x all squared. Of course, x start from 2 this time, because 1 ln 1 is 0, so you can adapt the 0 down the denominator. Again, argue. You see, this is continuous, because the denominator is never 0. This is positive, because x is positive, and ln of a number bigger than 2 is always positive. Of course, it is a square here, but in general, when x is bigger than 2, okay, so this means ln is going to be bigger than ln 2. ln 2 is 0.69, so it's always positive. It's decreasing because you see the bottom one is ln x. As x getting bigger and bigger, ln x getting bigger and bigger too. But this is the reciprocal of the bigger would be a smaller, okay? So the denominator getting bigger and bigger, so the reciprocal of that getting smaller and smaller. So the function is going to be decreasing. So you have to mention this. Again, f is continuous. F is going to be continuous, positive, continuous, positive, and decreasing. And decreasing where? When x is greater than 2 and positive infinity. That would be the limit of your integrations. Okay, so what we're going to do, we are going to look at the improper integral of this one. We check what's going to be proper integral from 2 to infinity, and then if that integral is convergent, so the series converges, otherwise it's going to be divergent, okay? And that integral is the one that we practiced before. Okay, so let's do it. So we're going to check how about this improper integral of 2 to infinity. Okay, checking 1 over x ln x, everything is squared dx. Okay, you check this one, you know the definition is going to be the limit of, you replace the infinity by t goes to infinity, integral of 2 to t, 2 to t, 1 over x ln x all squared. You have to find this integral. You can do it by u substitution. Remember we did it before, u equal to the ln x, or you can use the kind of shortcut to get these numbers. Okay, so decide what you want to do. So this is going to be basically 2 to t. You have to take it out, take care of the integral, and then go back and argue. So if you want to use your u substitution, your u would be ln x, and the du is going to be 1 over x dx. So we did it before, cross multiply, dx would be x du. Go to the integral, forget about this limit for the time being. So it's going to be 1 over x ln x all squared dx. So it's going to be integral of 1 over, you keep the x, ln x is u, so that would be u squared, times the dx, which is x du. So these two would cancel out. So that gives integral of 1 over u squared du. You know that this is going to be u to the negative 2 over negative 2. No constancy, of course. Then you turn it over. It would be negative 1 on the top and the 2u squared. Okay, but what is u? Remember, u is ln x. So that gives you 2 ln x all squared. Okay, now we go back and we check the integral from 2 to t. 2 to t, 1 over x ln x all squared. So it's going to be this integral. Okay, it's going to be negative 1 over 2 ln x all squared from 2 to t. If you substitute for the t, so that gives you negative 1, and that's going to be 2 ln of t all squared minus, now you substitute, it's going to be negative 1, okay, minus negative 1, 2 ln 2 all squared. You are not worried about the second part, because when you take the limit, ln of t would be infinity, this limit would be 0. Okay, so the limit of negative 1 over 2 ln of t all squared plus 1 over 2 ln of 2 all squared. You see, when t goes to positive infinity, this would be 0 because the numerator would be infinity. So you get a number. You get something like 2 ln 2 all squared. So this means you're not interested in the values, so just leave it as is. So this means, again, the improper integral diverges, and by integral test, okay, by integral test, the series sigma of 1 over, okay, 1 over n ln of n all squared. When n goes from 2 to infinity, this integral converges. Okay, converges, and you're done. So this would be a very, very typical problem, and you have it in various places. Okay, so in general, I give you the remark. Of course, you have to know how to prove it, but you can use this one in future. It would be very, very useful. You see, if this power is like a P series, if this power is going to be greater than 1, this integral is convergent all the time. This series is convergent all the time. If this power is less than 1, like 1/2 radical, square root, cube root, then this integral is going to be divergent. So it's like a P series. So I give you a remark, would be good for you to know it. But on the test, usually they give you one and then you have to prove it for us. Okay, so remark for future, because this is very popular integral. That's it. The series is like a P series, but it's not. The series sigma of 1 over n times ln of n, everything to the power like P, when n goes from 2 to infinity. You cannot have 1 because ln of 1 would be 0. Okay, this integral converges if P is greater than 1. Okay, and diverges, diverges otherwise if P is less than equal to 1. It's like the P series, but you should be able to prove it for us. One of the reasons that you study integral test really is to take care of these type of problems only. Okay, so such a important integral, such an important fact to know and be able, be able to apply it anytime we need it. Okay, so this can be used for some typical problems, integral tests, not all the time, but it is okay. It's very good to have this type of problems. Okay, so we give you more examples later, but that would be enough to take care of the integral test. Okay, so we are here. So we did the integral test. So that is section 11.11.3. Now we're going to continue bringing more tests for you. Okay, more tests. So this test that we are going to use can be used only if these terms of the series are going to be positive. So you may say, oh, what would happen if this is going to be negative? Then you have to wait to get these numbers. So we go to the 11.4 and we give you the most famous test really. This test is so useful. Okay, so what is going to be this test? This is going to be called, you see, that's going to be the one. We are going to call it comparison test. Okay, where is this is here. Okay, there are two types of tests. We call it comparison test, and we are going to explain it for you. What does it mean? Okay, so what is going to be a comparison? Okay, comparison tests or tests. Very popular test. So what's going to be this test? You see, There are some known series that we know it, especially the P series, okay, geometric series. We know everything about them. And we can quickly find out whether these tests are going to be convergent or divergent. So what we're going to do is sometimes another type of series would be given. This series may look like, P series or looks like geometric series. So what we're going to do, we are going to compare it with the geometric series or the P series. This type of operation would form these comparison tests, okay? So let's give you the condition of this test, okay? So it's going to be two series. The one that you are going to looking for it, okay, look to see if it's convergent or divergent. The other one is well-known P series, geometric series. Okay, there you are. Suppose these are going to be the case. Suppose sigma an, when we write nothing, it's going to be n from 1 to infinity. And sigma bn, they are series. Okay, this is going to be series with positive terms. With positive terms. Positive terms means this an and the bn must be all positive numbers. Okay, if it's going to be otherwise, we talk about it later. Okay, suppose sigma n, bn are series with the positive terms such that, okay, that's it, such that an is less than bn. Any an less than bn for what? For all n. For all n, then equal to the 1, 2, 3, etc. Okay, it's like, this sequence an is below the bn, So if this is going to be the case, then we are going to have the following, okay? If this happens, then the situation is going to be, okay, if, part one, if the bigger series is convergent. You see, convergent means if this is getting somewhere. The sigma of bn would be a fixed number, if you like. So we say that if the top is convergent, means we can cover the top, if you like. Then the smaller series will be convergent too. In order to remember it, you see if you can cover your house. So in that case, you can cover every room in the house. Or if you can cover the college, then you can cover each classes. Okay, so this is the way we remember it. So we say that if this second one is probably something that we know everything about it. Okay, it would be a very popular series. So if you know that if the bigger series, sigma of bn, if the bigger one converges, then the smaller one would be also convergent. Then sigma an is also convergent. Okay, so if the bigger one is convergent, means you cover the big one. So anything which is smaller, anything which is below the bn is also would be covered. Okay, so this is going to be one. The other case is the other way around. If sigma an is divergent, means you cannot cover the smaller one. Means this smaller one goes to infinity, if you like. If you cannot cover the smaller one, so how are we going to cover the big one? Okay, so this means if the smaller one, if sigma an is divergent, it goes to infinity, the series, okay? And then the bigger one would be also divergent. Then sigma bn is also divergent. Okay? The difficulty about this test is this is not two-sided. But we are going to change it in a minute, then you are going to have a two-sided one. But it's nice to know this one first. Okay? So this is going to be a situation that we have. I'm going to give a couple of examples first, then quickly I change it to something which is better. Okay, so let's see how we're going to use it, or when you realize that you have to use the comparison test. So you check to see if this series AN is similar to the one that you know, similar to the what, to the okay, to the P series, geometric series. Okay, so this is going to be the example. Example is going to be, we want to determine, okay, determine whether, again, you cannot find the sum of this series. You can just tell us whether the sum exists or not. Determine whether the series, okay, the series converges or diverges, Okay, let's check the first one. You see the first one is something like sigma of 1 over n squared plus 5. Look at this one. N from 1 to infinity. The way you think about it is check to see if this is going to be similar or like other famous series that you have. Or you see, we already talked about it. When it goes to infinity, you can shrink this one. If you shrink this denominator, so this would be like 1 over n squared. And you know that 1 over n squared is a P series with P equal to 2, which is convergent. So this one would be convergent too. This is quickly the way you are going to identify it. But you have to make that inequality for us, okay? So you compare it with the n squared. So how are we going to compare it? You're going to say that solution, and you say that you see n squared plus 5 is greater than n squared, because this is a positive 5. Now, if you use the reciprocal, so that gives you 1 over n squared plus 5, you have to reverse the sign. It's less than 1 over n squared, you see? So the bigger series 1 over n squared is convergent. So it means you cover the big one. If you cover the big one, the smaller one will follow. Okay, so now you explain that sigma of 1 over n squared, you know that is a P series, is a convergent P series, convergent P series. You know that P is equal to 2 and bigger than 1. And by comparison test, and by comparison test, the smaller one, sigma of 1 over n squared plus 5 is also convergent. So this is the way you are going to compare them together to get your result right away. Okay, so let's check another one to see how we're going to get this series. So you know it's going to be something like P series, so we can compare them together quickly to get the result. So, and we change it to the limit comparison test, which is much easier. Let's have another one. So what's in the other one? The other one is going to be this series, sigma of 1 over n plus radical n. You see, again, if you shrink it, this is n to the 1/2, this is n to the first. It would be shrink to the 1 over n. You know that sigma of 1 over n is harmonic series, is divergent. So this series should be divergent series, but you have to compare it to show us, okay, what is going to be the result. So solution is going to be, so this is n plus radical n. You want to compare it with the n. So how are we going to compare it to the n? You see the radical n is less than n. So this would be what? This would be less than equal to n plus n, because the radical n is less than n. So which is equal to the 2n, equal to the 2n. So what we have the fact that I repeat it again, n plus radical n is what is going to be less than equal to the 2n. If you use the reciprocal, it's going to be 1 over n plus radical n. The direction would be different, would be greater than equal to the 1 over 2n. But you know that sigma of 1 over 2n is less sigma of 1 over n is divergent. So this means the smaller one would be infinity. If the smaller one is infinity, this is bigger than infinity. So this would be infinity too. Or this means if you cannot cover the small room, how are you going to cover the building? Okay, it's the other way around. So you explain that sigma of 1 over 2n is a divergent p-series, is a divergent p-series. Divergent means this goes to infinity, this sigma. So when this goes to infinity, when it's a divergent, anything else would follow, okay? It's bigger than this. So you say that, and by comparison test, by a comparison test, you know, the bigger series, sigma of 1 over n plus radical n is also divergent. Divergent, and you're done. Okay, so it's very, very nice test. Very nice test. Okay, now we are going to change it into the format that we can have something which is two-sided. That would be much easier, because this sometimes you be confused which one are going to use, and most of the people will use it. So this modification would be make it so interesting for us. Okay, what is the modification? We are going to call it, the modification one is called the limit comparison test. What is limit? Okay, limit comparison test. Such an easy test. So let's see what's going to be limit comparison test. Again, suppose you have two series of the positive term. Okay, or you can say that suppose those general term an and bn are going to be our sequences. You can go with the sequence of series, sequences of positive numbers. Okay, and look at this one, and the limit of an over bn, n goes to infinity, limit of the ratio of these two series. This limit does exist, is equal to the L, we call it. Okay, so we find the limit of the an over bn, the general term, n goes to infinity, is equal to the L. Since these are the terms of the positive numbers, when you take this limit cannot be negative. So it must be 0 or greater than 0. Now, if this is greater than 0, not 0, okay, so if this is going to be positive, then you have something quite interesting. Then sigma an and bn, both of them can be convergent, or both of them can be divergent. So this means limit a series of an is convergent if and only if, you see, if and only if sigma of bn is convergent. Since it's if and only if, so if the, so similarly, sigma of an diverges if and only if sigma of bn diverges. So this means both series are going to be convergent, or both of them are going to be, okay, are going to be divergent. Very nice there. Okay, very nice test. And very easy to apply. I'm going to show you the shortcut for all of them, then you'll be able to take care of everything really so nicely. Okay, so the comparison by itself is good. Sometimes we need it, but this modification is much easier. Okay, to get these numbers done. So you have to find this Bn must be that familiar series. Okay, the familiar ones like a geometric one, or most of the time like the P series. And this is the way we're going to do it. I'll show you how quickly we can take care of everything here. Okay, so let's see. Example, check, determine. Determine if the series converges or diverges. Look how I'm going to take care of this series. The first one, the one that we did. Okay, just do it again. This is going to be the one. Suppose you have a sigma of 1 over n cubed plus 4. Okay, n from 1 to infinity. You see, this is the way we're going to do it. You are going to call this one an. You have to find, you see, this is going to be an, which is 1 over n cubed plus 4. Remember those shrinking one that we talked about it? So if you shrink the n cubed plus 4 to its leading term, which is n cubed, you get this series. You get the Pn, which is going to be 1 over n cubed. Okay, forget about the leftover, because when n goes to infinity, won't be, it doesn't matter. So this would make a sigma of 1 over n cubed for you, which is a P series and it's convergent. Okay, now if you divide, this is going to be the limit of an over bn. When n goes to infinity, would be what? Is the limit of n goes to infinity. So automatically you will get it. Is going to be what? So the top would be 1 over n cubed plus 4. The bottom one would be 1 over n cubed. You know that you write the first one multiplied by the reciprocal of the other one. 1 over n cubed plus 4 times it by n cubed over 1, n goes to infinity. Okay, so this is going to be the limit of, the top would be n cubed, the bottom one would be n cubed plus 4. N goes to infinity. You know that the powers are the same. So if you shrink it, that gives a limit of n cubed over n cubed. N goes to infinity, and this is 1. 1 is always positive. So the bottom one is sigma of 1 over n cubed is a P series. Therefore, the given one is also a P series. Okay, so you claim that 1 over n cubed is a convergent P series, and by limit comparison test, you have to mention the test, limit comparison test, sigma of 1 over n cubed plus 4 is also convergent, and be done. You see, this is the way we are going to operate. But all this operation can be written in a very easy form. To be able to see quickly, you should be able to take care of it. The way we do it is going to be, you see, in this format that we are going to have. Okay, you see, and just do it a quick way. You see, this is your an, is 1 over n cubed plus 4. Shrink it, it's like 1 over n cubed. See, that's 1. This is your bn. So if you divide them, You see, if you divide the limit when n goes to infinity, automatically this would be equal to 1. Okay, even you don't have to write it down, because this is it. You divide by bn. If you divide by bn, it's automatically 1. But you know, it's not bad to write this, but as I'm telling you in general. So it's going to be positive. It's positive, then the same argument that we have. Sigma of 1 over n cube is convergent, so the series is convergent, and you're done. Okay, so let's give one a little bit more involved to see how quickly you can take care of this series that we're going to have. Okay, so shrink it to find out. You must get something familiar. That something familiar would be the power series, the P series. Okay, let's give you another one to see how quickly we can take care of these. Okay, to get the numbers. Okay, let me go to the next page, give you something. Seems to be complicated, but I can do it right away for you. Which number is it? 2. Look at this one. You can make it as complicated as you like. I do it in a matter of seconds. Look at this series, n plus 5. N plus 5, the bottom one is what? Cube root of what? N to the 7 plus n squared. You want to see if this series is going to be convergent or divergent. Okay, so this is going to be your AN. Okay, this is your AN solution. This is AN equal to n plus 5 divided by the cube root of n cube plus n squared. You see, shrink it. When it goes to infinity, we talk about it. This is a polynomial in calculus 1, you know, this type of things. When it goes to infinity, the top would be, okay, when n goes to infinity, the limit of the top would be the same as the limit of the leading term. So the leading term is the term with the highest power of the n, it's n. For the bottom one, it's a radical. You go inside the radical, it's a polynomial, its leading term is n cubed. So this is going to be cube root of, okay, cube root of n, sorry, this is n to the 7. N to the 7, you see? So what you're going to do, simplify this one a little bit. So this is going to be what? This is going to be n. You see, this is cube root of n to the 7. You know that you can simplify it like in algebra. It's a cube root. So this is going to be what? If you divide the 7 by 3, that gives you what? You can write this one as n to the 6 times n. So this would be n on the top. N to the 6, you can pull it out of the radical. It's going to be 6 divided by 3. That gives you 2. So it's going to be n squared. Okay, the inside the radical, the leftover is going to be n. So these two would cancel out. So the final answer is going to be, you shrink it into what? The top is going to be 1, the bottom one would be n radical n. Okay, so it's going to be n squared. We simplify it. The top is going to be 1. Okay, and the leftover down the bottom would be n radical n. Okay, so this is going to be n. Okay, it's going to be n. And the cube, sorry, that's a cube root here. So it's going to be n cube root of n. Okay, so this is going to be a situation that you are going to have, and you know that this is going to be the power is 1. This is a 1/3. Okay, 1 plus 1/3 give you. You see, if you go on one step more, it's like n, and this is going to be n to the half, n to the 1/3. So it's going to be 1 over n to the 4/3. You know that it's going to be a P series and it's going to be convergent right away. Okay, so this is the way you are going to compare them together. So if you like, just go back, find what is the limit of AN over BN. Okay, when n goes to infinity. So it's going to be what? It's going to be the limit of your an is what? Your an is n plus 5 divided by cube root of n to the 7 plus n squared. You can divide it by the one that you got over here. It's going to be n. You keep the radical to be able to simplify it. You see? In future, you don't need it, but for the time being, you have to show us, okay? So this limit would be what? It's going to be limit of, the top is n plus 5, and this is going to be cube root of n to the 7 plus n squared times it by cube root of n to the 7 over n. Okay, put them together to find the limits. It's going to be kind of limit of n goes to infinity. Okay, you can think about this as n plus 5 here, and that's n. And these radicals, you see these radicals would be cube root of n to the 7 on the top, cube root of n to the 7 plus n squared on the bottom. Now when to take the limit, this would be 1 because n and n. This would be 1, and this would be 1 too because of these two parts which are the same as each other. So the limit would be 1, which is positive. Okay, the limit would be 1, which is positive, and we know that the bottom one, the series is convergent. Therefore, the given series is convergent too. Okay, so you just explain that the sigma of whichever you like. At the bottom one, you can go with this or the one that you simplify it. So we can say that the sigma of n over cube root of n to the 7 is a convergent p-series. Convergent p-series. And so the given series is convergent. Okay, sigma of n plus 5 over cube root of n to the 7 plus n squared is also convergent. Convergent. And then you're done. Okay, in future, for the time being, we wanted to do it for us. But in future, really, this is the way we do it. Look at this one. You shrink everything. This is the series. N plus 5. When we get towards after final, this is the way I'm going to do it, and I'd like you to do it for future. You see, you want to see what would happen to this series. Shrink this one. So it would be like sigma of, you shrink the top to the n, okay? You shrink the bottom into the cube root of n to the 7, you see? And as I simplify this one for you, remember n to the 6, I put it out. So that give me n. So that give me n squared. This is the way I simplify it. N squared, and that was what? And that was the cube root of n. N and n cancel out, so I end up with the sigma of 1 over n. And this is what? This is going to be n cube root of n. And you know that this is a convergent p-series. Because the power, if you want to go once more, as we did it, is 1 over n to the 4/3. So this is convergent. So the series converges too. And we done right away. Okay, so we do this type of operation for a little bit more time, but in future you must feel that this series is convergent. You see, as soon as you have a look at it, you just realize that it's going to be convergent, and you just do it right away. You're not going to stop to just to think about it or these type of ideas. Okay, but we practice to get to know them. Okay, so the AN and the PN must be p-series. Let's give another one. We practice and then you get it right away. Very good method. If you get to know it, you enjoyed it, and you have no difficulty. Let's take another one. Sigma of, there you are. n plus 1 over n squared. You want to check the series is going to be convergent. Check to see what's a familiar series that you have. Okay, you shrink this one. You see when you shrink it, what you get. You see it's n over n squared, which is 1 over n. So you have to compare it with the 1 over n. So this is an, which is n plus 1 over n squared. If you like, compare it with the n, shrink it. So that gives you 1 over n. So you call your bn 1 over n. See, this is the way we do it. Now take the limits to confirm it. Limit of the an over the bn, n goes to infinity, is equal to the limit of n goes to infinity. An is n plus 1 over n squared, and this is 1 over n. You write the first one, multiply by the reciprocal of the bottom one. You see, that's a limit. N goes to infinity, so what's the top? It's going to be limit of n goes to infinity. If you multiply, this is, okay, you can simplify it by n, that give you n. So we get n plus 1 on the top, and when it goes to infinity, you know that this limit would be 1 because of the n and n. And the 1 is bigger than 0. So again, the bottom series is divergent. So we say that the sigma of 1 over n, n from 1 to infinity, is harmonic series, is a divergent P series or harmonic series, and by limit comparison test. Limit comparison test is the way we write it down. LCT, the given series n plus 1 over n squared is also divergent. See, this is the way you do it. Quickly, we can take care of it. Okay, so you can have various form. Really, I give you one more radical so that you see that it's not going to be difficult. Give you another one. See this one, sigma of n over a square root of what? A square root of n to the 5th plus 4. That's it. You shrink it. You shrink the top into the n. The bottom one is going to be a square root of n to the 5th. You see this one? So this is going to be your bn. So your an is what? Your an is given n over a square root of n to the 5th plus 4. You pick the bn to be what? The bn to be n over radical n to the 5th. If you simplify that, give you n. This is n to the 4 times n, so it's going to be n squared radical n. You simplify that, give 1 over n radical n, which is convergent, you know that. It's going to be n to the, okay, it's going to be n to the what? 1/2 and 1, 3/2. So what you do, form that fraction, but when you form it with this so that you'll be able to find the limits right away. So you know that your series is convergent. When we are out of this section, this is the way we do it. So the limit of an, the details, is going to be equal to what? The limit of an, n square root of n to the 5th plus 4. Write this one because it would be easy to simplify now. N over n to the 5th, n goes to infinity. So it's going to be equal to the limit of n goes to infinity. The top would be n square root of n to the 5th plus 4, reciprocal, radical n to the 5th over n. You see, automatically limit would be 1, because this is radical n to the 5th, and this is radical n to the 5th, and this is n and n. In fact, n and n would cancel out. So what you have is the limit of radical n to the 5th and this is radical n to the fifth plus 4. When n goes to infinity, they are like each other. So it's a 1 bigger than 0, that's it. The bottom series, as you know, it's convergence. Say the sigma of 1 over, okay, 1 over that, this one. Okay, the bottom one is going to be, you see, sigma of n over n to the fifth. Say that it's convergent, is a convergent P series. And so the given series, sigma of n over n to the fifth plus 4 is convergent. And we're done. Okay, this is the way you are going to use the limit comparison test. It's a great test, really. And then it can be applied everywhere. And as I told you, in future, we do all this operation. In future, if you see this one in calculus 2, you must feel that, you shrink it right away. Because everything you do, you see, let me just do this one once more to show you what we are going to do out of this quiz that you're going to have. You see, look at this one. In future, this is the way you are going to tell us. You see, sigma n over n to the fifth plus 4. We ask you whether this is convergent or divergent. You say, oh, if I shrink it, that give me n. This would give me n to the fifth. Okay, then this would be sigma n. N to the fifth is n to the 4 times n, so it's going to be n squared, radical n. Okay, sigma of n would cancel out, that give 1 over n radical n. You know that this is what? This is sigma of 1 over n to the 1/2, and 1 would be 3/2. Is a convergent P series. So the given series is convergent by limit comparison test. The given series is convergent, and you're done. You see, this is the way we operate in future. Because we know that in the limit of a and b, and you divide, you get 1. Because you have it here, you see. If you divide both sides by 1 over n to the 3/2, the result is 1. So the limit is 1, is never 0. So you get the convergent series right away. Okay, we shrink it, we get it, and then we are not going to worry about it. This type of ideas that that we are going to have. Okay, I didn't give you something with the geometric series. Let's give you another one. Let's take this one. You want to know whether this series is convergent or not. Okay, so something like, how about 1 over 2 plus 3 to the n? See, look at this one. If you shrink this one, you see, 1 over 2 plus, it's like you can forget about the 2. It's 1 over 3 to the n. You know this geometric series, common ratio of 1/3, less than 1, convergent, done. But you can use the limit comparison test or just the comparison test. That would be very easy to check. Okay, solution. You say 2 plus 3 to the n is bigger than 3 to the n. If you use the reciprocal, 1 over 2 to the 3 to the n is less than 1 over 3 to the n. That's it. The bigger one is convergent. So you cover the school, so you cover every room. So you explain that sigma of 1 over 3 to the n is geometric series, is a geometric series with the common ratio of r equal to the 1/3, less than 1, it converges. You see? So by comparison test, the given series, sigma of 1 over 2 plus 3 to the n is convergent. You see, when it's a geometric, this is the way you are going to take care of it. Excellent test, very good one. You give me any series you like, I can do it right away. So you have to shrink this series first. You see, like the one that I did here. You shrink it as much as you can. Because n goes to infinity, you see the top and the bottom would be the same as the leading term, n with the highest power, n. Inside the radical, highest power, n to the fifth. So a square root of n to the fifth, you know that n to the fifth is n to the fourth times n. N to the fourth, the square root of n to the fourth would be n squared. You simplify it, so that you 1 over n radical n. Radical n is n to the half, times n would be n to the 3/2. It's a p-series, it's convergent. You see, you want the limit comparison test. This is bn, this is an. Limit of the an, you divide. You see, divide this one by 1 over n to the 3/2. Automatically, when you divide, the other side would be 1. So the limit would be 1. It's not 0. The bottom series is convergent. So your given series would be convergent too. And then automatically, okay, automatically you are done. Okay, so this is 11.4 limit comparison test. So we are here so far. Okay, so we did the integral test. And the comparison test is here. If the an and the bn, if the bigger one is convergent, the smaller one is convergent. If the smaller one is divergent, the bigger one is. This would be confusing, but you better use the limit comparison test. The limit comparison test, you find the limit of the an over bn. If this limit is positive, both of them are convergent or both of them are divergent. Very easy test. Okay, so these are all the tests that we have for the positive series. Okay, so that would be enough for tonight. Then I give you another one. The next question is going to be, what would happen if this term of this, because this test, you see, you need an and the bn to be positive numbers. So what would happen if these terms are not positive? Some of them are negative, some of them are positive. So we have 2 more tests for them. So I give you another one during the week. Then we take care of that one too. So then all this table would be covered. Okay, so by the end of the week, we are going to learn all the series, but it takes time because the other one's going to be more involved. Okay, so have a good one and have a look at it. Okay, and then we are going to continue and we give you as many examples as you like, and at the end some shortcut, and then you'll be fine. Okay, that's it. Have a good one and take care. Bye-bye.